calculation of the load for the baseboard heater is performed by multiplying the length of the heater in feet by its wattage per foot. In this scenario, 11.5 feet of baseboard heater rated at 300 watts per foot results in a total load of 3,450 watts. To determine the current draw, the total wattage is divided by the voltage. With a 208 volt supply, 3,450 watts divided by 208 volts equals approximately 16.6 amps. Since baseboard heating is considered a continuous load, the National Electrical Code, or NEC, requires that the circuit be sized at 125% of the continuous load. This means multiplying the calculated current of 16.6 amps by 1.25, resulting in 20.7 amps. Therefore, a 25 amp 2-pole breaker is appropriate for this circuit. To determine the appropriate conductor size, refer to NEC Table 310.16. This table provides the ampacity of various conductor sizes based on their insulation type and installation conditions. For a 25 amp breaker, 2 number 12 American wire gauge or AUG conductors are sufficient, assuming they are copper and have an appropriate insulation rating such as THHN, THWN, or similar, and are installed in accordance with the table's conditions. The grounding conductor size is determined by NEC Table 250.122, which specifies the minimum size of equipment grounding conductors based on the size of the overcurrent protection device. For a 25 amp breaker, a number 10 AWG copper grounding conductor is sufficient. It is important to understand that the grounding conductor's purpose is to provide path for fault current back to the source in the event of a ground fault, not to carry normal load current. Therefore, it does not need to be larger than the ungrounded or grounded conductors, often referred to as hot and neutral wires, respectively. The correct wiring configuration for this circuit is 2 number 12 AWG conductors for the ungrounded and grounded conductors, and a number 10 AWG copper conductor for the equipment grounding conductor. It is a common misconception that the grounding conductor needs to be larger than the circuit conductors. The grounding conductor size is based on the rating of the overcurrent protection device, as specified in NEC Table 250.122, to ensure it can safely carry fault current. To summarize, firstly, calculate the total load of the baseboard heater by multiplying its length by its wattage per foot. Secondly, determine the current draw by dividing the total wattage by the voltage. Thirdly, increase the calculated current by 125% to account for the continuous load requirement. Fourthly, select an appropriate breaker size based on the adjusted current. Fifthly, refer to NEC Table 310.16 to determine the appropriate conductor size for the ungrounded and grounded conductors. Sixthly, consult NEC Table 250.122 to determine the appropriate size for the equipment grounding conductor. Finally, install the wiring in accordance with all applicable codes and regulations. When selecting conductors, consider the insulation type and temperature rating. Common insulation types for branch circuit wiring include THHN, THWN, and THW. Ensure that the conductors are rated for the temperature conditions of the installation. For example, if the conductors are installed in a hot environment, a higher temperature rating may be required. Also, ensure that the conductors are properly sized for the voltage drop in the circuit. Voltage drop can cause appliances to operate inefficiently and can even damage equipment. The NEC recommends limiting voltage drop to 3% for branch circuits and 5% for feeders. To calculate voltage drop, use the following formula: voltage drop equals 2 times K times I times D divided by circular mils, where K is the constant for the conductor material, typically 12.9 ohms circular mils per foot for copper, I is the current in amps, D is the one-way distance of the circuit in feet, and circular mils is the circular mil area of the conductor. Select conductors with sufficient ampacity and voltage drop characteristics to ensure safe and efficient operation of the circuit. Remember that electrical work can be dangerous and should only be performed by qualified individuals. Always follow all applicable codes and regulations and take appropriate safety precautions. Before starting any electrical work, turn off the power to the circuit at the breaker and verify that the circuit is de-energized using a voltage tester. Wear appropriate personal protective equipment, such as safety glasses and gloves. If you are not comfortable performing electrical work, hire a qualified electrician. When working with electrical systems, it is essential to understand the difference between grounded and grounding conductors. The grounded conductor, often referred to as the neutral wire, provides a return path for current under normal operating conditions. It is typically connected to the neutral point of the power source, such as the transformer. The grounding conductor, also known as the equipment grounding conductor or EGC, provides a path for fault current in the event of a ground fault. It is connected to the metal enclosures of electrical equipment and appliances and is intended to carry fault current back to the source, tripping the overcurrent protection device, such as a breaker or fuse. The grounded conductor is intentionally grounded at the service entrance, while the grounding conductor is connected to ground at multiple points throughout the electrical system. The purpose of grounding is to provide a low impedance path for fault current, which helps to protect people and equipment from electrical shock and damage. In addition to equipment grounding, there are other types of grounding systems, such as system grounding and static grounding. System grounding refers to the grounding of the electrical system itself, typically at the service entrance. Static grounding is used to dissipate static electricity, which can build up on non-conductive materials such as plastic or rubber. Static electricity can be a hazard in certain environments, such as those where flammable materials are present. Proper grounding is essential for electrical safety. Always ensure that electrical systems are properly grounded in accordance with all applicable codes and regulations. When troubleshooting electrical problems, check the grounding system to ensure that it is intact and functioning properly. A faulty grounding system can cause a variety of problems, including electrical shock, equipment damage, and fire. To properly size electrical circuits, one must consider various factors, including the load, voltage, conductor ampacity, overcurrent protection, and grounding requirements. The load is the amount of electrical power that the circuit is expected to supply. It is typically expressed in watts or voltamps. The voltage is the electrical potential difference between 2 points in the circuit. In North America, common voltage levels include 120 volts, 208 volts, 240 volts, 277 volts, and 480 volts. Conductor ampacity is the maximum amount of current that a conductor can safely carry without overheating. It is determined by the conductor size, insulation type, and installation conditions. Overcurrent protection is provided by breakers or fuses, which are designed to trip or blow when the current exceeds a certain level. Grounding is the process of connecting electrical equipment and systems to the earth, which provides a path for fault current in the event of a ground fault. The National Electrical Code, or NEC, provides detailed requirements for sizing electrical circuits. The NEC is a set of standards developed by the National Fire Protection Association, or NFPA, to ensure the safe installation of electrical systems. It is updated every 3 years and is widely adopted by states and municipalities throughout the United States. When sizing electrical circuits, it is important to consult the latest edition of the NEC and to follow all applicable requirements. Failure to comply with the NEC can result in electrical shock, equipment damage, fire, and other hazards. In addition to the NEC, there may be local codes and regulations that apply to electrical installations. These codes and regulations may be more stringent than the NEC and must be followed in addition to the NEC requirements. It is important to check with the local authorities to determine what codes and regulations apply to electrical installations in a particular area. The sizing of the equipment grounding conductor, or EG, is crucial for ensuring electrical safety. The EGC provides a low impedance path for fault current to return to the source, allowing the overcurrent protection device, such as a breaker or fuse, to quickly trip and clear the fault. The size of the EGC is determined by NEC Table 250.122, which specifies the minimum size of the EGC based on the rating of the overcurrent protection device. The EGC can be a wire, a conduit, or other metallic raceway. It must be connected to the metal enclosures of electrical equipment and appliances and must be properly bonded to the grounding electrode system. The grounding electrode system consists of one or more grounding electrodes, such as ground rods, metal water pipes, or concrete encased electrodes, which are connected to the earth. The grounding electrode system provides a connection to the earth, which helps to stabilize the voltage of the electrical system and provides a path for fault current to dissipate into the earth. The installation of grounding electrodes and bonding connections must be done in accordance with the NEC requirements to ensure that the grounding system is effective and safe. Proper grounding and bonding are essential for electrical safety. They help to protect people and equipment from electrical shock and damage and help to prevent fires. Always ensure that electrical systems are properly grounded and bonded in accordance with all applicable codes and regulations. When performing electrical work, it is important to use the correct tools and equipment. Use insulated tools to protect yourself from electrical shock. Wear safety glasses to protect your eyes from flying debris. Use a voltage tester to verify that circuits are de-energized before working on them. Use a circuit finder to identify circuits in a panel board. Use a wire stripper to remove insulation from conductors. Use a crimping tool to crimp connectors onto conductors. Use a multimeter to measure voltage, current, and resistance. Use a ground tester to test the integrity of the grounding system. Using the correct tools and equipment can help to make electrical work safer and easier. Always follow the manufacturer's instructions when using tools and equipment. Do not use damaged or defective tools or equipment. Inspect tools and equipment regularly to ensure that they are in good working condition. Store tools and equipment in a safe and secure place. Electrical safety is paramount when working with electrical systems. Always take the necessary precautions to protect yourself and others from electrical shock, fire, and other hazards. If you are not comfortable performing electrical work, hire a qualified electrician. Remember that electrical work can be dangerous and should only be performed by qualified individuals. Before starting any electrical work, turn off the power to the circuit at the breaker and verify that the circuit is de-energized using a voltage tester. Wear appropriate personal protective equipment such as safety glasses and gloves. Follow all applicable codes and regulations and take appropriate safety precautions. By understanding the principles of electrical circuit sizing and grounding, and by following safe work practices, you can ensure the safe and efficient operation of electrical systems. The information presented here is for educational purposes only and should not be considered a substitute for professional advice. Always consult with a qualified electrician or other professional before performing any electrical work.